Mr. Kuswidyastuti, STMPPSD.
Yang kami hormati Bapak Ibu tim penyangga, yang kami hormati Bapak Ibu para undangan. Assalamualaikum warahmatullahi wabarakatuh. Selamat siang dan salam sejahtera bagi kita semua.
The Honorable all the examiners, ladies and gentlemen, the attendees, peace be upon you and our mercy and blessings. Good afternoon and greetings to all of us.
Bapak Ibu hadirin yang berbahagia, puji syukur kita panjatkan kehadirat Tuhan karena pada hari ini Selasa 26 Juli 2022 kita semua dalam keadaan sehat dan dapat menghadiri acara sidang terbuka promosi doktor atas nama Saudari Devy Kuswidyastuti.
Ladies and gentlemen, we thank God for today, Thursday, July 26, 2022. We are all in good health and can attend the doctoral promotion competition for Devy Kuswidyastuti.
Pada kesempatan ini, Promovenda akan mempresentasikan disertasinya dengan judul Novel Multi-Beam OFDM MIMO Radar with Circulating Codes.
On this occasion, Promovenda will present her dissertation with the title Novel Multi-Beam OFDM MIMO Radar with Circulating Codes.
Bapak Ibu hadirin yang berbahagia, sebelum acara sidang terbuka promosi doktor ini dibuka, marilah kita dengarkan sambutan dari Ketua Komite Pertimbangan Fakultas yang diwakili oleh Bapak Kuswidyastuti SDMTPS. Pada beliau dipersilahkan.
Ladies and gentlemen, before the presentation of the doctoral promotion opens, let's listen to the speech from the Chair of the Faculty Advisory Committee, represented by Mr. Kuswidyastuti, SDMTPS.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. First of all, we welcome to the Honorable ITS Rector or Representative, Dean and Vice Dean FDEIC IPS, all then Representative, Head of Department in FDEIC IPS, representing Professor Dr. Yuyu Wahyu from Pusat Riset Telekomunikasi BRIN as an external examiner, chairperson of the session, supervisors and examiners, colleagues from Promovenda, the family of the Promovenda, and all guests. Today, Tuesday, July 26, 2022, there will be an open session of doctoral promotion from Promovenda, Devy Kuswidyastuti, NRB 07-114-6001-0001, who will present a dissertation entitled Novel Multi-Beam OFDM MIMO Radar with Circulating Codes, appointed from her dissertation entitled OFDM MIMO Radar with Circulating Codes. Closed exams from Promovenda have been held previously on Monday, July 4, 2022, and passed. Dear ladies and gentlemen, we need to inform you that the doctoral promotion session was carried out by the Faculty of Electrical and Intelligent Information Technology, FDEIC ITS, in this case, the Faculty Advisory Committee, based on the ITS Rector Regulation in 2017 concerning the Commission for the establishment of the faculty in the 10 November Institute of Technology. The session is required to provide an opportunity for the Promovenda to explain these results, which are scientific works with all their scientific contributions. The promotion sessions is the accountability of the postgraduate program education to the public. That a new doctor has been produced who can work as an independent scientist, has a good scientific knowledge, scientific insight, and sufficient ability and attitude science. This promotional session is also useful for introducing a new doctoral candidate and their application to the related scientific community. Okay, to Mr. Chairperson of the doctoral promotion session, we invite you to preside over the promotion session this afternoon. And our audience, let's attend the doctoral promotion session this afternoon. Finally, we apologize profusely if there are things that are not pleasing and convenient to all of you. Wassalamualaikum warahmatullahi wabarakatuh.
Demikianlah sambutan Ketua Komite Pertimbangan Fakultas yang diwakili oleh Bapak Kuswidyastuti SD MD PhD. Untuk selanjutnya, marilah kita ikuti jalannya sidang terbuka promosi doktor ini, di mana sidang akan dipimpin oleh Ketua Sidang Terbuka Promosi Doktor kepada Doktor Insinyur Wirawan DE. Dipersilakan.
This is the speech of the Chairperson of the Faculty Advisory Committee, represented by Mr. Kuswidyastuti SD MD PhD. For the next, let us move the doctoral promotion open session, where the session will be led by the chair of the doctoral promotion open session, Dr. Insinyur Wirawan DE. Time is yours.
Okay, please allow me to open my mouth. Selamat siang, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. Today we gathered here in this room to attend the academic session for the doctoral promotion of Promosi Devy Kuswidyastuti to present research works based on investigation during the PhD study, doctoral study. As the chair of this academic session, I hereby declare that the session is open. Okay, thank you. Next, I will read the achievement by Promosi before this promotional doctoral promotion session. So, before she present today research works on the doctoral promotions, the Promosi has conducted close examination, oral examination, attended by all the examiner, external examiner as well as internal examiner, and also attended by the promoter and co-promoter. The oral exams defense has been conducted on Monday, July 4th, 2022, and all the examiner, if I can read all the examiner here, the promoter and co-promoter, Professor Insinyur Samantio Indrantoro, MPhD, PhD, and the co-promoter, Professor Dr. Honoris Causa Insinyur Leonardus P. Likhar, and the three examiners, the two internal examiner is Dr. Insinyur Titik Sediani, MP, and the second internal examiner is Dr. Insinyur Jandayani, MP, and the third examiner comes from the outside organization. Professor Dr. Nisio Yudi Wahyu and they from BRI. Okay, so it means that the Provenda has completed the required requirement before presenting his her research work in this doctoral promotions. Next, I would like to invite the promoter to the stage to read the curriculum vitae of the Provenda. Okay, please, Professor Amanda. You could use this one if you'd like. Okay.
Okay.
Thank you, Mr. Chair. I will read the very short biography of the author. Devy Kuswidyastuti, currently a student member at the IEEE, was born in Gresik, Indonesia in September 1981. She received the BEng degree, Bachelor of Engineering degree in Electrical Engineering from Institute of Technology 10 November, ITS, in 2004. And then she joined R&D Engineering Department at Panasonic Shikoku Electronics Indonesia in 2004 to 2006. Afterwards, she decided to continue her study and obtained the MSc degree from Hochschule Darmstadt, Germany, in 2008. She works as a lecturer at ITS and she is currently pursuing the PhD degree at ITS Indonesia. Her current research interests include MIMO radar and array signal processing. Okay, thank you.
Okay, thank you, Professor Sumanjo. Okay, next I will invite the Provenda, Ms. Devy Kuswidyastuti, to enter the room and to present research work for in this doctoral promotion. Please have a seat. Okay, we will present your research work in 30 minutes. And please pay attention that the audience are not only in this room because we have also external examiner rather than using Zoom by online. And I will remind you maybe 3 or 2 minutes before the end of the allocated time that you maybe you cannot finish on time. So you can start now. Thank you.
Thank you very much, Dr. Irawan, for the time. Ladies and gentlemen, good afternoon. Assalamualaikum warahmatullahi wabarakatuh. Today I would like to present my dissertation with title OFDM MIMO radar with Circulating Routes. Its promoter is Prof. Kamantio and Prof. Devy. Okay, for the outline of today's presentation, first one is introduction, and then I would like to explain some fundamentals of OFDM MIMO radar, and then the transmitter design, ambiguity function analysis, and receiver processing, and then the conclusion. For the introduction, the background and motivation of this research is based on the modern radar requirements. which is not only for target detection and ranging, but now radar must have the feature to have the ability to also for tracking, identifying and classifying these targets, and also for at the same time suppressing the signal of clutter, jamming and any other unwanted signal. A large part of the radar system is based on digital domain. For example, the digital waveform generators part and the digital signal processors. And then radar nowadays is for modern radar. It's not just a simple pulse radar. You see the picture now. It is a conventional radar that probably you could see it in the airport, where the radar is spinning in mechanical. And nowadays the modern radar is not necessarily have to turn in mechanical, but actually the beam is scanning. And then what a modern radar have is a digital waveform which generates signal, which can be done by software. So that is including the generation of phase and amplitude of each element of phase array. And then when we do this, then we could eliminate the phase shifters, and we could also reducing the requirement for power dividers in this case. And then we could have a low side load level waveform, beam characteristics, yes, which we could design directly from the waveform that will be transmitted from the multiple elements. And then, why we use multiple transmit and receive antenna systems, MIMO radar, for circulating load? Yeah. Because in here we use the multiple antennas to have beams which can with a narrow beam width, and that will involving large arrays with a lot of phase shifter per element. Then that would cause a high production cost. And here, if we use MIMO and CC, circulating code, we could eliminate the requirement to have a lot of phase shifter per element, because we could provide the phase difference that is needed for the antenna element directly from the waveform. This is already done by previous researcher, Babur and all. MIMO with CC, but with LFM. But in here, we try to develop the new one, which using OFDM signal. And then digital beamforming can be accomplished at both sides, at the receiver and the transmitter, by using a digital waveform generators and digital signal processors at each of the antenna elements. This will make the production cost lower because we don't need the phase the phase shifters, and also we also don't need to have an amplitude and phase control device. And then the CC or phase control can be generated as part of the digital waveform. Then why we try to develop CC MIMO with OFDM? Because we knew that OFDM has advantages. It has a flexibility in the management of its spectrum component. And then we could have a specific scheduling by dividing the total available bandwidth become several subbands. Yeah. And we could also implement easily coding at the OFDM subcarriers. Then that feature allows us to have multiple orthogonal beam signals, which transmitted simultaneously, and then we could also have multiple symbols with different codes that we could transmit successively, and then we could also have a radar which have a variable pulse repetition frequency. Yeah? We could use this to see the amplitude and phase variation of the received signal over a short or long period. And the main advantages there compared to LFM that OFDM have is that it doesn't have a coupling at its range and Doppler detection. And then how to design a CCRDM radar system with so this is the problem statement of my research, my dissertation, is how to design a CCRDM radar system with multiple orthogonal narrow beams pointing at different angles simultaneously and continuously over a wide swath of angular direction. And this is done to increase the time on target and accuracy of the target detection, without having to have a costly phase and amplitude control. And then we will transmit the orthogonal waveform in series. This is done so that we could have a higher signal to noise ratio to detect target which is at a long distance. And then for low transmit power without degradation in maximum analysis range, this can be done to achieve a low probability of intercept data and to allow a cheaper solid state amplifier. The proposed concept is that we combine the privilege that we have in MIMO and OFDM. We could use the combination to have multiple beam scanning, which can scan like a array. But actually, what we did here is not beam scanning, but beam forming. Because if beam scanning, then the beams are scanning at a certain duration period. But in here, the beam is transmitting continuously and simultaneously at the same time. And we could do that without the need of phase shifters because we designed the OFDM waveform by having a scheduling in the subband and then the code to have multiple beams by taking advantage of the flexibility in the sub-carrier management and exhibit the orthogonality and lower PRPR when their sub-carriers are coded properly. Orthogonality between beams by division of the total OFDM bandwidth. We divide the total available bandwidth into subband, which result in so the range resolution per beam is depend on the bandwidth of this subband. Each subband will consist of several subcarriers which are responsible for making a beam to a certain dimension. Here we will have a multi-dimensional orthogonality in time, frequency, and space, which is provided by the codes and by the subband scheduling that we have decided. Then the fundamental of the CCRDM MIMO radar basically can be described as follows. So we have a multiple antenna that transmit and receive. This is the block diagram. The left one, if we look, there are several transmitters there with several antennas, and each of the antennas are transmitting a coherent signal. The same signal is transmitted from each of the antenna, and only different by the increment multiplication of delta t. Delta t here is the delay signal. There's a small time delay signal which is transmitted from the multiple antennas, and when they are combined on the air, they will create a beam which will pointing at a certain direction. And the left one is the representation on the time domain, and then the right one, the right figure is the illustration if we see it on the phase domain. It is uniform linear array with array factor that we'll describe later on the next. Yeah. So the array factor of the OFDM MIMO radar here. Basically, we could say that it is similar to the classical array factor, only that here we have a component which is the waveform effect, and then the other one is the array radiation effect. So the waveform effect, that was the effect that is caused by the waveform that we generated, and the array radiation effect will depend on the array arrangement of the array antennas. Yeah, so we will have to give a phase difference to the antenna element in order to creating a beam at a certain direction. Yeah, and this phase will be provided by the waveform, by the OFDM waveform, so that the signal, the generated signal, which comes to the multiple elements, when it is combined, it will create a beam at a certain direction. Yeah. So because we are dealing with an OFDM signal, which is basically a multi-carrier signals, so when we give a phase difference to a signal with a certain frequency, it will create a beam at a certain direction. But because we are dealing with multiple carrier signals, if we give a constant value of beta, or a phase difference is constant, then eventually we will have a beam that it is squinting from the original direction, because it is a multi-carrier frequency. And we try to overcome this. There are three ways, but we propose the third one. The first one is by using less subcarriers. But if we use less subcarriers in each subband, that means we will have to lose some quality on the range resolution. So if we strictly follow to some specification which related to the range resolution, we could not use this method. And then the second one is that we could use a higher band, but that will mean we also have to have a high requirement on the clock accuracy of the systems. And then the third one is that we implement, or we apply a phase correction to the subcarrier frequency, so that the beam is not squinting, but it acts to only pointing to one direction. So if we see here, the left one is when we have a beam squinting. You can see that the color represent the signal frequency of OFDM signals. And if you could see at the left side is when we have the beam, the multiple beam without any correction to the subcarrier phase. Then you could see that the array factor has three different curves. It is a little bit squinting from the others. And then the right one, you could see that the beam squinting is not there anymore, because we already applied phase correction for beam broadening. So the subcarriers at the same subband is directing to the same angle direction. For the transmitter design, this is the specification of this radar. So it is operated at 3 gigahertz, yeah, with a bandwidth around 20 megahertz, and then the beam width of the azimuth, which we discussed, which we focus on this research, is 1.3 degree. Yeah. And then what else? Okay, OFDM simulation is 0.1 milliseconds. So and we want to have range detection, the maximum unambiguous range of 180 kilometers. So we will need to transmit 12 symbols successively to have to extend the maximum unambiguous range to up to 180 degrees. And this is the block diagram for the TR module of OFDM MIMO radar system. As you can see, so in one block here, it is TR module, which are connected to each of the antenna azimuth. So we have 101 antenna element at the azimuth because we want to have a beam width of 1.3 degree. We need as much as 101 elements. And then because we apply the phase correction for each of the subcarriers that we transmit, that will require that the waveform generator is also at each of 101 transmitter which connected to 101 azimuth element. So first, starting from digital waveform generators. Here. And then we generate digital signal, and then going to the digital analog to analog converter, and then half conversion. Here, half conversion is done analogically from 20 megahertz IF frequency to 200 megahertz, and then going up again until RF frequency 3 gigahertz, and then going to a power amplifier. The signal is amplified, and then going to a power divider, circulator, and then goes to 21 element of the elevation elements, antenna elements. And then the receiver starts the signal received from 21 elements will be combined, and then goes to the down converter change, yeah, from RF to IF2, yeah, which is 200 megahertz, and then goes to 20 megahertz, and then after that going through an analog to digital converter, and then it is processed in a digital signal processor. And this is what happened in the waveform generator. Basically, it is OFDM generator, signal generator, yeah? And we have 8 subbands in these systems, which each subband consists of 256 subcarriers, yeah? And then we will use these 8 subbands to have 63 beams, yeah? Which are orthogonal because it is coded with a different coded code. And then we generate these signals and transmitted simultaneously the 63 beams from 101 transmit elements. And the combined signal will create multi-beams, which is 63 beams, yeah, to be precise, that have a low side lobe characteristic, yeah, because in here we use amplitude tapering for lowering the side lobe of the beams. We use Taylor amplitude tapering. You could see that if we compare with the uniform amplitude distribution, we get the blue one is when we use Taylor, we have a side lobe level is lower until minus 30 dB. Yeah. But we could also see that we sacrifice a little bit beam width there, because when we use uniform, the beam width is 1 degree, but if we use a Taylor, yeah, the beam width is wider. It gets around 1.3 degree, but it still can satisfy the requirement for surveillance method. And this is the scheduling for the 63 beams. Yeah. So you could see that the color here are describing the subband. Yes. So every row is for a specific beam. We will use 3 different subbands for one beam, and then we transmit 12 successive signals for each beam. Yeah. So these 63 beams with different subband and different codes will be transmitted simultaneously and continuously from 101 transmitters. And as you can see, because we only have 8 subbands and we need 63 beams, that means we have to reuse some of the subbands. Yeah, we have to reuse the same subband 8 times. So each subband will carry 8 different beams. Yeah, and you could see that the color is repeated. Yeah, every 8 consecutive beams. Why 8 consecutive beams? Because we consider that after 8 beams, yeah, the spatial distance between the beams is long enough, is far enough, so the coupling is low because we have a low cycle characteristic on the beams. Okay, so this is the 63 beams that we could get by implementing the scheduling, and also the amplitude tapering. We get the low cycles, and then we also have a narrow beam width that as the required surveillance method that we get. Then we also discuss about the PIPR, because we know that OFDM signals have the nature that it has a high PIPR. So here why we choose polycode, because besides that the polycode is orthogonal, it also have a special characteristic that it has a low PIPR. That is why we use polycode, and we could say that for the 63 beams, yeah, from the 12 symbols, we could see that the PIPR is for the 12 symbols always less than 8 dB. Then the ambiguity function. Basically, the ambiguity function is like an autocorrelation function. Yeah? So we could see in this equation that actually it is a correlation between 2 signals. Yeah? And here we have the OFDM signals, and then the code, the Golay code, and also the amplitude tapering that we use, which is Taylor distributed. Yeah? And then here probably we could skip the equation and go to the result. Yeah. So from the previous equation, we could make the plots for seeing how the characteristic of the systems that we design. Yeah? The first, the left one, yeah? The 2 figure on the left is actually the ambiguity function. If we see it on the domain of the theta and the theta 0, it could, from this figure, we could see that the beams, the 63 beams that we have, it is orthogonal to each other. Yeah. That is why the figure is diagonal there. And then for the middle picture is the function. There's a function of tau, and theta. Theta is the direction of the target, and then tau is the time delay, or round trip delay, because rather actually we calculate how many time delay that needed for a signal, which is reflected back by the target back to the radar. So if you see tau there, basically it is the information that we use for range detection. And the figure at the right, if we look at the middle figure and see it only from one dimension, we could see the range resolution and the beam resolution. If you see that it is analyzed from the broadside beams, which is around 0 degree. The beam width is around 1.3, and then if you look at the maximum scan angle of around 45 degrees, 44 degrees, you could see that the beam width is around 1.7 degree, and this still can fulfill and satisfy the requirement of surveillance radar. And the range resolution is around 60 meters as the required mission requirement.
You have 3 minutes.
Okay. And this is the coupling analysis. Because we use multi-carrier signals, and we use some of the signals, so we have to analyze how much coupling that happens. So you could see that the coupling is very much low for even for neighboring beams, the beams that are near to each other, or for the continual beams, or the beams that are using the same socket. So this is the transmit additive scheduling that we have. So we have one mode for low power mode. So the transmitter is transmitting low power signal, so that the receiver can active at most of the time it is active, and then stand by for receiving the signal. And then the second part is when the radar is operates at 2 modes. One is the low power mode, and the other is high power mode. For low power mode for sharp range detection, and high power mode for long range detection. And this is for the receiver. We have to skip this one. And then this is the parallel processing. So we receive the signals, and then we combine the received signals, and then correlate the signal with the signal reference that we have, and then we could calculate we could estimate the target beam direction, and then the target range. And after we have 32 frames of 12 symbols, we could estimate the Doppler frequency. Okay, this is the result of the range and detection from the correlation, and then this is for the Doppler processing. We could get the Doppler estimation from seeing the phase variation of the acousticness. Okay, so this dissertation describes the implementation of CC in agile scanning MIMO radar, and then you can produce a beam towards a certain angle by applying appropriate delay difference, and then we adopt the OFDM waveform in CC MIMO radar coupled with spectrum division into subband and then orthogonal codes to make multiple beams, and then we could solve the beam squinting problem by having a phase correction, and in general the design, the radar design can fulfill the requirement for the desired resolution and efficiency in beam range Doppler for any target within the applicable range and RCS in the entire area field. And that's it. Thank you very much.
Okay. Thank you, Professor. Ladies and gentlemen, for the next steps, we will move to question and answer from the examiners, as well as from the team of Promosi. Okay, for the first presentations, I would like to invite the external examiner, Professor Yudio from Pusat Riset Telekomunikasi from BRIN, to pose his questions first. So please pay attention because the question will be given in online. Okay, from you, if you are ready, you can give your question. Thank you.
Hello.
Yes, it's clear.
Can we hear?
Yeah, it's okay.
Okay, thanks to the chairman of the Open Doctor Promotion Examination, Dr. Devy. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. The Honorable Professor Mandio, our teacher, the professor who inspired radar technology in Indonesia. Okay. First of all, I congratulate Mrs. Devy for your achievement up to this open research. Alright, I have the three questions for the doctoral candidate, Mrs. Devy. First question, please explain what is the fundamental difference between the phase radar and the MIMO radar you before. Okay. Number two, the second question, in the slide showing slide number 17, the transmit or is transmit receive module or PRM, the antenna is not a song. The whole width is 21 times 101 antenna. So it does not solve the coefficient of its TRM connected to the antenna. The question, is the TRM connected to one antenna? If yes, how to control for the vertical beam and horizontal beam? The third question, in my opinion, the TRM that you have developed is the TRM which is more advanced than conventional TRM, when one of its features is to change the phase in the form of the hardware into a time delay is done in a software. My question, is it possible that we can master the TRM technology that we develop without mastering a conventional TRM technology? That is my question. Clear?
Okay, thank you. Professor Yu, is it clear?
Yes, I will try to answer.
Okay, you can start now.
Okay, for the first questions, what's the difference between the CCO and the MIMO radar with the phase array radar? For these questions, the difference are, so for phase array radar, the beams are,
Could you please stand up?
for the phase array radar, the beams are scanning. So the beams are scanning, and in this dissertation, the beams is not, we cannot say that it is scanning because the beams is transmitting simultaneously and continuously at the same time. So it is not scanning, but it is like a beamforming at the same time. So it will have a larger time on target because the beams is not scanning. And then the other advantages, I think, which is also related to the second question, is that the phase difference that we need to directing a beam, we develop we provide that from the time delay difference, which you already mentioned. And because we use OFDM signals, it is possible to have that delta T value and give it. It is not provided in the time delay, in the time domain of the signals, yeah, but we give that at the frequency domain of the OFDM signals. So we like giving the phase difference, which corresponds to the specified delta T, to the subcarriers that we use for transmitting those signals. And then regarding the TRM of this radar, yeah, as you could see from the slides number 17, yeah, that you already mentioned, that the TRM here, if you look at the part with the red box on the right side, which is a TX, transmit and receive analog up and down converter, is actually just like the conventional or any conventional radar. Yeah. It is a simple TR analog up and down converter. So what if you said that can we do this without mastering the TRM conventional? No, we still need the TRM knowledge, yeah, because from the analog part, for the analog chain, up converter and down converter, it is basically work on the same as the conventional radar. What we have developed is at the digital part here, that we should have a complex digital waveform generator and also a complex digital signal processor. And how to control the vertical beam and the horizontal beam, if you were saying about how we change the direction of the beams, we could do that simply by giving, by setting the value of delta T, which we give that phase difference to the subband, which are used to transmit the beam, and then we could get the beam direction that we want. And then if you is this TRM connected to one antenna or multiple antenna? So in here, each of this TR module is connected to one azimuth element, antenna element, and that one TR module is connected to 21 elevation element. And then I think that's it for the second question. And I think it also solved the third one.
I don't know, I'm not sure. The question is it possible to master TRM without mastering?
Yes. I think I've already answered that because we have the analog part is basically just like the same conventional radar, but what makes it modern radar is what we do in the waveform design and what we do in the signal processing of the received signals. So for the analog, we could use the knowledge we have from the TRM of conventional radar, but for the digital part, we have to develop a new one, which is the implementation of this design.
Okay. Thank you.
Okay, thank you.
Okay, thank you, Professor Liu.
I return to Pak Wirana.
Okay, thank you. Next, I'll invite the internal examiner, Dr. Titik Suryani, to give questions. Please.
Yes. First, I want to thank to Dr. Wirawan as the chair of this event, that is doctoral promotion, who has given me the opportunity to ask some questions. And also, I would like to congratulate to Devy, who has reached the stage of completing the doctoral studies. And now I have 3 questions. First question is for the next future works, which part of that openly needs to be investigated in more details, and why it's more need to investigate. Second question is why in the waveform design, especially for the circular code and cooling codes, you use a block of subcarrier which are consecutive objects. In my opinion, it will be when beams coming from target to the receiver of the radar, it's more robust to the intercarrier interference because of Doppler. If we use not in consecutive object. And the third question is why on this OFDM MIMO radar you omit the cyclic prefix that is commonly used in the OFDM technique. Is it because this is similar to the circular code? Yes.
That's all. Okay, thank you. I said, here for you for
Yes,
questions.
I will try to answer the
Okay, please.
questions. So the first one is related to the future works that should be done after this research. So actually, now my research has arrived to the receiver processing, and then we found out that when we do because we generated the signals digitally at IF frequency, and then at the receiver, we try to do the correlation also at the IF stage of the signals. So we correlate 2 IF signals, and we found out that when we do this, we will have, especially for the Doppler, we will have a high interference from the IF frequency, because the IF frequency is 20 megahertz and the Doppler frequency is around 1 kilohertz. So the difference frequency makes that the phase variation is dominantly caused by the IF frequency instead of the Doppler frequency, which we want to estimate is the Doppler frequency, so that if we want to have a proper best Doppler detection, we should remove first the IF effects of the to the echo signal before we do the face processing to get the Doppler information. I think that will be the first one that should be solved after this. And then
Is there a most urgent one?
yeah, I think so. And then after that, perhaps we could think of how to start implementing this design. Probably started from because it is focused on the waveform, so I think it's better to start implementation from the waveform generator. So how we could generate the OFDM signals which have CC on it and which have a code on it, and we also have to consider the requirement for the clock oscillator that we should choose to have the signals that could to have a waveform generator that would generate signals which have a small time delay between the multiple transmitters. That I think that's the first feature works that should be done. And then for the second one, I hope I understand it correctly. Why we did circulating codes and used the design for one subband, one block of it, because in radar the bandwidth of the signals will determine the range resolution of the radar systems. That is why we divide the total available bandwidth 20 megahertz. We divide that into 8 subbands because from the specification of the radar we need a range resolution of 60 meters for surveillance radar, and we could get that by having signals which have a bandwidth of a minimum of 2.5 megahertz. And in this case, then we should have a block of subcarriers which have a spacing of 10 kilohertz, and then that will make for each subband we will have 256 subcarriers, which will have a total bandwidth for one subband is 2.56 megahertz. That will give a range resolution of 60 meters for each beam. And then you suggest that we don't use successive subcarriers in this case. I'm not sure because we haven't done that. Because I know that if we did not use consecutive subcarriers, probably we will get, in communication, probably we will get a better performance in Doppler resolution. But if we look at, probably that would be easy if we could track the processing at the baseband level. Probably it could be implemented. But if we do it at IF, I'm not sure if that is applicable. But because we haven't tried that, but it is before we do that, I think it is better that we found out first how much intercarrier interference that will happen, because in these systems we have everything on the ideal condition. We still don't have interference, don't give any imperfections to the systems. So if we want to apply something to solve each problem, we should first probably find out how much severe is the ET to this system. And then if it is severe enough, probably we could consider to use the idea of having not a block of software, but parsing the softwares, and that could be used for other purposes also in the system. And then the last part, why did we omitted the cyclic prefix? Because I think we've done the research where at first we use the cyclic prefix, but it cannot be applied because we transmit the symbols successively in series. Yeah. So we cannot use the cyclic prefix in this order because if I'm not mistaken here, if we use cyclic prefix, we add cyclic prefix and then at the end we remove the cyclic prefix. And in this design, because we use successive symbols in series, if we remove the part of the cyclic prefix, we will lose some part of the signals, which probably important for the range detection. I think that is why we don't need the cyclic prefix in this case. I think that's all.
Okay, thank you.
3 questions.
Yeah. Okay. Next, for the last examiner, I would like to invite Dr. Kuswidyastuti to ask the questions.
Thank you, Dr. Gunawan. Especially, I want to say congratulations to Devy for receiving the okay. In this occasion, I have 2 questions. More about the geometry of the area antennas we use. The first is for surveillance radar with 360 degrees horizontal coverage. How is the area antenna should be designed? Because in the example you consider in the dissertation, you use 90 degrees of horizontal coverage. So, what kind of geometry will be used if we want to cover 360 degrees? So, and the second question is, if we want, this radar is also the function for be used for tracking function. Is it necessary to change the design of the array antenna? Is it necessary to change the design of the antenna? And if so, how is the modification? Thank you.
Okay, thank you.
Okay, thank you very much, Dr. Puji. I'd like to answer the first one, which is related to the array. How does this design can be implemented for 360 coverage? So yes, in this design we only have a coverage of minus 45 degrees until up to 45 degrees, and we purposely design it that way so that if we need to have a 360 degrees coverage, that means we will need four of this radar. One is for coverage from So 360, that would be like 4 domain of 90 degrees. That means that we have this radar system for one domain, one which covers 90 degrees, and then we have another 90 degrees, and then we have another 90 degrees, 90 degrees, and we will get a full circle of 360 degrees coverage in this. Yeah, and then for the next one, for tracking target, do we need to change our arrays? I don't think so, because probably we could, yes, but we have to add more design to the design, because in now in current design we only want to have the feature for surveillance, which means the beams are directed to a certain angle that we design to cover, to have coverage there. And then if we want to track a target, we could do that by pointing our beam to that target. How can we could change the beam direction by changing the delta T value that we have for beamforming. So we could change the direction of the beams as we want it, as we need. Yeah. So we could do that by changing the delta T value by software. So we don't have to change the hardware of the radar. We could simply do it by changing the software in this case. Of course, it will need some additional algorithm for tracking, because we have to follow the target, but it is possible to do it by changing the beam design from the software part. So if you see the TR module from the digital waveform generated from the digital part, that should be we should add some more design which is related for tracking features. I think there is two questions.
Yeah. Okay, thank you. Okay, next we move to the team of promoter. First, I'd like to invite Professor Lihat to ask his questions. Okay, please.
Thank you very much, Mr. Chairman. Devy, it is a good moment to reflect. It remembers me that in the beginning you had a challenging subject and you had multiple hypotheses and sub-hypotheses facing novelties for a PhD project. In the end, you have in chapter 7, you have the list of novelties. And there I see that from the 10 hypotheses you had in the beginning, you have now 11 novelties. Okay, so that's a good result, and I was seeing with pleasure that you did a patent submission. And therefore my first question is, what is really the key novelty in your dissertation? The key, the most important. And related to that, is that coming into the patent request? If not, why not? Okay, then you had many more novelties they know their future? And if you have answered these questions, I'm still wondering what should be the sequence for patenting of your work. Thank you.
Patenting.
Okay, thank you very much. The difficult one. Okay. I think the most important novelty in this dissertation is that we apply CC with the OFDM, which has never been done before. So the previous research that related to MIMO CC is with LFM, and then they implemented the delta T at the time delay of the signals, but in here we implemented the phase difference delta T at the frequency domains of the OFDM signals. I think that is new. And then in here we also have a special scheduling. In here we transmit 12 successive symbols which are coded with orthogonal codes. Usually when we have signals which have for one symbol we have a signal with a time duration of 0.1 milliseconds. We only have a maximum unambiguous range of 15 kilometers. With this design, because we could have coded signals, so it is possible to transmit 12 symbols successively and then have the extension of the maximum unambiguous range, which when we have only one symbol, we only could reach 15 kilometers. So with 12 symbols, we could reach up to 180 kilometers, and we could go even further. So the flexibility is the main novelty, I think, in this system, radar system, because we could create our waveform according to our need. I think that would be the most novel and most interesting part of this research. And
Is that in the patent?
yes, I think it is. It is on the patent.
Okay, that's all.
Yeah.
Thank you. The last part, I'd like to invite the promoter, Professor Doktor, to give his question.
Thank you, Mr. Chairman. I have three questions. First of all, thank you, congratulations for getting at this stage, which is almost the final for your doctoral study. So I have three questions. The first one, your OFDM MIMO radar is currently still at the conceptual stage. Yeah? So if you want to realize a prototype of your of the OFDM MIMO radar, what's okay, so if you want to realize a prototype of the OFDM MIMO radar, what steps do you think you should take? That's the first question. Two more questions are more general. The first one, now if you... Okay, the second question is, okay, now since you already finished your dissertation in OFDM MIMO radar, I would like to know
how the roadmap of your future research look like? Yeah. Okay. So that's the second question. The third one, you are a lecturer in the electrical engineering department in AS. Yeah. So you have students, of course. Yeah, many students. My question is, how are you going to develop motivation of your students so that they are interested to learn about radar? Okay, so that's all I have to say.
Thank you.
Thank you very much. The first one is related to prototype. Okay. For prototype, what I should do first. Okay. I think we plan to have a simulator for this radar. So before we implement something, perhaps it is better to have first a simulation, so that we could learn what to expect when we implement this in the hardware or in software. So if that's the first one, I think, and then the second one probably it is related to the prototype. I think as I answer for the static questions, I think it is better to start from the waveform generator part. In this case, we also have discussed this, but haven't got to there. Related how we implement waveform generators by using USRP. In that case, we should check whether USRP specification can be used as the waveform generators of this radar. That is the first thing I think that should be validated. And then if we could use USRP, then we could start, making a small scale first. I think it is impossible that we make 101 elements. That means we will need 101 USRPs. I don't think that is reasonable, because we will need the budget also for this research. And then, probably for the small scales, I think probably has also mentioned, probably we could start by having eight elements for starting to implement these radar systems, step by step. I think that is the first one. Then for the second one, roadmap. Okay. Roadmap. So okay. That would be also the roadmap for this research. I think we could continue the research because everything is ideal for now. So we haven't investigated what will happen if we have interference, if we have noise or anything that is imperfect. So what happens if we have a clock oscillator which is not phase locked to each other? What will happen? We haven't investigated that. So perhaps that could be on the roadmap. And then prototyping is also on the roadmap. And then what else? And then we could design. Perhaps we could see how we could implement this system for monopulse radar. We could do that, and then in this design we only have the scans in azimuth. Perhaps we could develop also in the education. Then there are a lot of possibilities to further research on this area. And then for the lecture, how to attract students. Yeah. So for that, we should give a lecture on class, which is not boring first, and then we should motivate them that it is possible that we design our own radar, because sometimes we expect, it is like something that we could not do ourselves, because it is something that very, very expensive. But we could start by small research first. We could explain on the class on how we design radar systems, and perhaps giving them some small project regarding radar system design. Then they can go in groups probably, so they give them special taste for radar. I don't know. It can be anything.
Okay, yeah. Okay, thank you very much. Okay, now ladies and gentlemen, we have concluded the part of presentation and oral examinations. Before we move to the next stage, I would like to invite you to take big applause to the commentator. Thank you for having presented the very nice presentation and reflect the having answered all the questions given by examiners. Next on the agenda, I will recapitulate all the achievement, and as well as academic requirements that has been obtained by the Promopenda so far up to date. Okay, we have witnessed previously that the Promopenda has given the summary of our research works during the PhD study, and she has also successfully and satisfactorily answered all the questions given by the examiners as well as by the promoters and promoters. And before arriving at this stage, as I have mentioned previously, the Promopenda has also achieved and obtained all the academic requirements so far. So I will read them to you. The first is that the study that has been conducted by the Promopenda, she has accumulated 42 credits from the required 40 only, and she has conducted successfully the oral exam previously on July 4th, 2022, and she has obtained the notes of A, the maximum, yeah, for the oral exam. And as you know that apart from the courses and also the dissertation that she has to complete it, there are some other academic requirements, administrative requirement that has been that must be obtained. The first is publications. So the Promopenda has published a paper in the Journal of IEEE Access entitled "The Transmitter Design for the Multi-Beam Circulating Code OFDM Remote Scanning MIMO Radar." and it has been accepted on May this year. And the antibody assets is a journal with Q1 ranking. And secondly, he has also published 2 publications on the international conference. The first one is given in the IEEE International Conference on Aerospace Electronic and Remote Sensing on 2015. And secondly, in the International Conference on Communication Networks and Satellite, or ComNetSat, in 2016. And apart from that, the Promopeda has also submitted a patent in the National Register with the title of the patents in bahasa Indonesia, sistem radar jarak jauh dengan sonor jamak serta menggunakan teknik circulating code OFDM. And the date received in the patent institution is on March 22, by 11 March 22. So once again, she has published 1 article in the National Journal and 2 publications in conference and 1 patent. Next, another requirement for the study of doctorate, she has also obtained the required level of competency in English. She has obtained certificate of Doktor. So that's all the required academic requirements that has been all satisfied by the Promopeda. Next step, then the graduate program study from the electrical engineering department will report this result to the KPF, or in English is Faculty Advisory Committee, which will decide the graduation, the title, create doctor to the Promopeda. Okay, that's the part for the recapitulations of the PhD study, doctoral study of the Promopeda. Next, I will move to the speech, another speech. The first, I will invite to the stage the co-promoter, Professor Richard, to give some encouraging parting speech or whatever you want. Please.
Thank you very much, Mr. Chairman. I will remove my mouth cap. Okay. And my earache. Actually, today is a fabulous day. Groups have seen the start of a new generation radar. I can say that because I have only experience of more than 40 years in radar. And today, it was not only for the world an important day, but also for Devy. So dear Devy, you reached a milestone in your career. Your PhD project is ended with a dissertation which should lead to the graduation to doctor in technical science. My hearty congratulations. Looking backwards on your project, I can tell you that your experience fit very well in the experience I have with my other 58 PhDs who I supervise as a After 6 months to a year, you finish your literature survey and stated that several scientists have done serious work on OFDM radar. You raised the question, is there sufficient novelty for me to do a PhD project on OFDM radar? My answer was yes, and now your dissertation is full of novelty, and derived from these, a series of advances of the OFDM radar have been described. You are now an expert in OFDM radar, and your material is really at top world level. You cannot find that in a literature. Most of the things are important for future development in OFDM radar. And be aware and become public. Be aware, you should become working in projects and you should do publications. Publications who has laid the basis in your PhD project. I know I am a demanding advisor. I was demanding, raising many questions. I was seldom fully satisfied, so I always raised more questions. But in all those years, especially during my visits to ITS, you never complain. You never complain. Now, I only can wish you success in your future career.
Next, I will invite Professor Hamanto, Doctor as a promoter, to give also his speech.
Okay, thank you, Mr. Chairman. My speech will probably be more funnier in bahasa Indonesia, so I would like to mix both languages. Okay, selamat Bu Devy. Tidak terasa selama studi Bu Devy sudah banyak yang terjadi sehingga sampai saat ini sudah bisa lulus. Translation is it okay? Congratulations, Dr. Devy Kuswidyastuti. Finally, you completed your doctoral study. You finished it like a marathon runner, slow at the start, and then speeding towards the finish. Selama menempuh S3, ada beberapa rekor yang sudah dicapai oleh Bu Devy. Pertama, Bu Devy telah mengalami masa 3 rektor yang berbeda. Okay, so in English, I noted that you were studying in the doctoral program under 3 different rectors. But you study with the same president. You still have the same. Sebagian dari putra-putri Bu Devy lahir pada saat Bu Devy baru memulai studi S3. Mereka mungkin mengira bahwa mahasiswa S3 adalah pekerjaan Bu Devy. Dan bahwa acara kita hari ini adalah acara perpisahan Bu Devy yang pensiun dari pekerjaan mahasiswa S3. Okay, in English. Some of your children were born when you were just starting your doctoral study. As a result, they may think that their mother's job is being a doctoral student. And then this event It's a farewell party because you are retiring from the job. Oke, di lain pihak adanya dua anak, dua putra putri yang lahir selama Bu Devy studi S3 mungkin adalah indikator dari tingkat stres yang dialami. Okay, so from another point of view, having two children born during your doctoral study may be an indicator of the level of stress. So, as a conclusion, it has been a very hard fight. Yeah. So, yang jelas, okay, so I will start with English then. But I think above all, your family must be very, very proud of you. Your children should be proud to have you as a role model, especially in doing your study. They will be motivated to study as high as their mother has done. Yeah. And for ITS, I think ITS will be beneficial to have you as a new doctor. And I hope in the future you could contribute more, not just to ITS but also to the society. Yeah, because I actually quoted this from Professor Ritard's saying that every research should, in the end, have something useful, beneficial for the society. Yeah. So I hope you could contribute more also to the development of the science and technology, especially in the fields of radar. So, and also because you are also a lecturer, I hope you could motivate more students to learn about radars, because now in Indonesia, especially there are still a few students actually interested to learn about radar. So I think I would like to congratulate you and wish you success in the future career as a doctor. So after this is I think the end of my speech, not very long. After this, I would also like to hear your own speech as a response to our speeches. Yeah. Okay, so again, congratulations, Dr. Kuswidyastuti.
Okay, thank you, Professor Kamantio, Doktor. Last but not least, that is not the final speech because I'd like to invite the Promopenda herself to come forward. And after all, the suffering and what she has been through, she has entitled. Yeah, so either you can speak or give some speech or sing anything you want. And maybe you'd like to share here with your colleagues, maybe with some students, also your family, about your study. Okay, you can start.
Okay, thank you very much for the opportunity. First of all, I would like to express my deepest, highest gratitude for both of my promoters, Prof. Lihat, Prof. Kam. I don't think that I can manage to arrive at this point without their guidance, without their advice. And you said that you are very demanding. Yeah. Because, at every meetings, I think I have cold feet.
I didn't know.
I don't think it is shown on the face, but it happens. But I think it is for the better. I think from every questions that you raise, I begin to think, yeah, where did that coming from? And then I start to learn more and more things from there, and not just about the radar systems or anything related to the research, but I also learned a lot of things about life. And probably you don't realize, but I did learn something from you, and many things I think about how we should work hard then how we should appreciate others' time. Yeah, I found that very precious. And also for Prof. Gam, I can express my highest gratitude. You always remind me, come on, you should write your report. Prof. Gam, Prof. Lithan is waiting. And then I also want to thank Mrs. Lithan, because she's always there in one of our meetings. Because Prof. Lithan won't be here if Mrs. Lithan is not coming. You come here during the pandemic that's still going on. So thank you very much. And also to all of my colleagues, thank you very much. Dr. Fitri, Dr. Puji is also we discussed a lot about this research, and I hope if we continue to have this research, I hope that we could cooperate and collaborate more in radar, if you don't mind. Perhaps I know you involve mostly in communication systems, but I hope that I could also drag you to the radar systems. And then also to all of my friends and colleagues and my families, thank you very much. I have some of my families attending this at this venue. My husband, my father, my sisters, and my sister-in-law, and then my brother-in-law and my nephew. My niece. Yeah. Thank you very much for the support. I would have been here without the support from all of you. Thank you very much.
Okay, thank you. It's very pertinent. Emotional. Okay, now we are really in the last part of the sessions. On behalf of the graduate study program of Electrical Engineering Department, we'd like to thank you for all the examiners, Professor Buyu Wahyu from BRIN, Dr. Titi Suryani, and also Dr. Puji Handayani, as well as most importantly, of course, the promoter teams, the promoter Professor Doktor and also Professor Lithan. Okay, and also all audience in this room, as well as in the online attendance. Thank you very much for your attendance today. Okay, before I return to the stage to the organizing committee, I'd like to declare that the session is now officially closed. Okay, thank you very much. Now I return to the stage.
Hadirin yang berbahagia, tibalah saatnya pada acara pemberian ucapan selamat. Pemberian ucapan selamat akan diwakili oleh Ketua Sidang, diikuti oleh Ketua Komite Pertimbangan Fakultas, dilanjutkan oleh tim penyangga, tim pengamat dan para undangan. Untuk itu kepada saudari Doktor Devy Kuswidyastuti beserta keluarga dipersilakan berada di depan mimbar untuk menerima ucapan selamat dan sesi foto.
Ladies and gentlemen, it's time for the congratulatory session that will be initiated by